Hello, this is Professor Thad Starner. Today we're going to talk about digital to analog converters. To do this, we're going to use simple resistor ladders to do the conversion to analog. Let me talk about digital analog converters for a second. You can think of these as what takes the bits off your CD player and converts it to voltages that you can hear in your earphone. So your CD is spinning around. It has the bits for your songs all on the CD. Your microcontroller reads that, the microcontroller in your CD player. And once it reads the values, it's then got to change those digital values to analog. And how it does that, it has a bit for each of the 16 bits, a line for each of the 16 bits for the music. And it then combines those bits into one of 65,000 plus values, and those values then go to your headset. And how that works is something like this. This is a resistor ladder, and this is a R2R digital analog converter. Now, why it's called R2R is that it's simply made up of resistors of value R and resistors of value 2R. And you can put whatever resistors you want in here as long as it doesn't draw too much current or draw too little current. Now, your microcontroller, in this case, say a PIC or an Atmel, is up here in a big block and might have the least significant bit, bit 0, bit 1, bit 2, bit 3, bit 4, bit 5, etc. on out to bit 16. I have only 4 bits here. Now what's neat is that you can actually get the value of the voltage out here by a simple formula. You look at the digital value as specified by these bits, multiply it by your reference voltage VCC, and divide by 2 to the number of bits, and that's going to be your voltage. So, for example, if none of the bits on the microcontroller are set, the voltage out is going to be VCC times 0 over 2 to the 4 in this case, 16. V out is 0. If the least significant bit is set, then the digital value is 1. It's VCC times 1 over 2 to the 4th, which is 16. In other words, the value, the voltage out is VCC over 16 for a digital value of 1. A value of 2, bit 1 here is set, and looking for the formula, we have VCC times 2 over 16, or VCC over 8. You can keep on doing this the whole way up to the table. The highest voltage you're going to get is when all the bits are set, in this case, a digital value of 15, and you're going to get 15 times VCC over 16, as we saw here. Now, this seems like a really complex circuit. Do we really believe this formula? Let's take it one bit at a time to see if we actually can understand what's going on here. Let's start with a 1-bit R2R digital analog converter. Now, not that that makes much sense, but it's a way to start out. So in this case, I only have V out coming from between these two resistors, R1 and R2. Now this is the same as if we're just looking at the left side of this circuit, right? We're only going to make a 1-bit system, so that's all there is to this circuit. We have 1 bit on the microcontroller and ground. Now, this looks like and is a simple voltage divider. R1 and R2 are both 2R from what we saw in our original circuit. Of course, when bit 0 is 0, V out is 0. When bit 0 is 1, though, we have a voltage divider, but since R1 and R2 are equal, they're both 2R, it means that V out is basically just VCC over 2. Now if we look, that seems exactly what the formula said. VCC times the digital value of 1 in this case over 2 to the 1 bit, so VCC over 2. Well, that's great. So it works for a 1-bit R2R digital to analog converter. Now notice that I use DAC for short. Most people in electronics know when you say DAC, it's a digital to analog converter. Let's look at something a little bit more complicated. Let's look at a 2-bit R2R digital analog converter. In this case, we have 2 bits on our PIC or whatever microcontroller you're using going into the 2 different resistors. Now these are the same resistors here. We're just looking at the last 2 bits of our original circuit. And for convenience later on, I'm going to label each of the resistors as R1, R2, R3, and R4. Now, we could do this as R1, R2, 3, 4, 5, 6, 7, 8, on to 16, and then coming back the other way, and the last one would be like R33. But we're just doing a 2-bit R2 RDAC, so we're going to keep it simple for now. And you can see down here I've labeled it as R1, R2, and R4 are all equal to 2R, and R3 is equal to just R. Now our formula here that we're using predicts the following. When bit 0 is 0, bit 1 is 0, the value is 0, and V out should be 0. When bit 0 is 1, sorry, I should not have flipped these here. When value is 1 for the circuit, V out is going to be, let's see here, our formula says V out equals VCC times val, it's a 1 over 2 to the 2, so that means it should be 1/4 VCC, so VCC over 4. When bit 1 is high and bit 0 is low, that means we have a value of 2, and we expect it to be VCC of, a V out of VCC over, let's see here, 2 over 4, so VCC over 2, half VCC. Now when bit 0 and bit 1 are set, we have a digital value of 3, so again we should have 3 times VCC over 4. Okay, so that's what the formula says. Let's see if we believe that.